Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. In finite element analysis, meshing is very important because better the mesh, better is the solution. If we want to achieve convergence criteria, then we need to go for meshing and remeshing again and again. When the result is not varying, we can say that convergence criteria is obtained. Hello viewers, today I'm going to show finite element analysis of a chimney using ANSYS mechanical APDL. In this analysis, I'll show two different types of analysis method. One will be with structured meshing and another will be with normal meshing method. Let us see the statement of the problem. Determine the temperature distribution and the rate of heat flow per meter height of a tall chimney whose cross-sectional area is shown in the figure. Assume that the inside gas temperature is 211 degree Kelvin. Convective heat transfer coefficient inside is 68.14 watt per meter square degree Kelvin. Surrounding air temperature is 255 Kelvin and the outside convection coefficient is 17.04 watt per meter square degree Kelvin. Let us see the drawing. This is the drawing, right? So first of all, we analyze this one using ANSYS mechanical APDL using structured method. While performing structured analysis, we can see that the object is symmetric along x-axis and y-axis both directions. So if we divide the object into 1/8, then we can find some specific area. As a result, obtained from all of these cases will be equal. Right, this is the chimney, this is a rectangular cross section, right? Inside the rectangular cross section we have another annular space of rectangular area, right? So this is actually 4 meter, this is also 4 meter, and inside this one this is having 2 meter, right? In this analysis we are considering this part as the main part, because if you divide this one, it will be having symmetric areas of this part, right? It will have symmetric areas of this much of cross section in all sides. So if we divide this one, it will be having 8 segments of this type of cross sectional areas. All will be having similar areas as it is a symmetric one. So for analysis, we'll take this is the only segment and we'll perform the analysis, because the remaining 7 segments also will be having same, because all are symmetrical, right? So without wasting time, let us start our analysis using this segmented method. We will be considering only 1/8 of this segment, right? Let us understand this one again. A equal to 4 meter and this B equal to 2 meter. So we are starting from here, some gap is there. So this from here to here is 1 meter and from here to is actually 1 meter. So these are the different nodes. While modeling this one, if you are moving along x direction, you have to move 0.5 meter, and if you are moving y direction also in this way, you have to move 0.5 meter. In x and y both direction, you have to move 0.5 meter, right? So accordingly, we'll make the different elements, making actually a total 7 numbers of elements and 12 numbers of nodes. Okay, let us start analyzing using ANSYS mechanical APDL. First of all, we need to create a directory, and in the directory everything to be saved. Next to that, we need to change the title of this one, and we are keeping the title of this one as FEA 15. To see the title, we can click plot replot. It will show the title at the lower left corner, right? Next to that, we need to select what type of analysis it is. It is a thermal analysis. So thermal analysis is checked in. Okay. Next to that, we need to provide elemental properties, and it will come from preprocessor. Element type, add, edit, delete. Let us add it, and we are considering solid quad 4 node 55. Okay. Let us close it. Now material properties to be provided. Material properties, material models, thermal conductivity, isotropic, and thermal conductivity is 1.7307 watt per meter degree Kelvin. So we can provide this one 1.7307 watt per meter degree Kelvin. Okay, let us close it. Next to that, we need to start modeling, and modeling to be created, as we told before, we need to create nodes, right? Let us create nodes in active coordinate system, and as I told before, we need to form 1/8 of this chimney cross-section areas. So as I told before, we need to start from specific location. Along x direction, it will be started with 1. Apply. The next node will be at a distance 1.5 meter. Apply. And in this row, the last node will be at a distance of 2 meter. Apply. Next, we need to move up. So along y direction, we need to move up at a distance of 0.5 meter, and along x it will be 1 meter. So along x it will be 1 and y it will be 0.5 meter. Apply. Next one, along x it will be 1.5 and y will be 0.5. apply. In this row, the last one will be x equal to 2 and y equal to 0.5, apply. Again we need to move to the next row. Along y it will be 1 meter, and along x also it will be 1, apply. Next node will be along x it is 1.5 and y it will be 1, apply. And in this row the last node is 2 and y equal to 1, apply. Now we need to go for the fourth row. It will be x equal to 1.5 and y also equal to 1.5, apply. Next node in this row, x equal to 2 and y equal to 1.5, apply. And the last node it will be at a distance of x equal to 2 and y equal to also 2. Okay, so the nodes are created. Now with this node we need to create elements, right? So it will be started with elements auto numbered through nodes. We can join nodes like 1 2 5 4 to create the first element. 1 2 5 4, apply. First element is made. Now second element will be comprising of nodes 2 3 6 5, select 2 3 6 5, apply. Second element is made. Now the third element 4 5 8 7, apply. Fourth element 5 6 9 8, apply. Fifth element 7 8 10 and 10, apply. Eighth element 8 9 11 and 10, apply. Sixth element is made. Now the last element will be comprising of node numbers 11 12 10 10. So join node numbers 11 12 10 and 10. Okay, we made these whole elements and it is comprising the 1/8 of the whole segment. The areas are actually symmetric, so whatever result will be obtained in this area, that will be symmetric for other cases also. It is actually simpler meshing method. In this way we are making structured method, right? And our meshing is complete. Next to that we need to apply our boundary conditions, and that will be done from loading, analysis type, new analysis. It is a steady state analysis and we need to define loads, right? Apply thermal convection on nodes. In the boundary condition it is applied that inside temperature is 311 Kelvin, and from there the heat transfer is occurring by way of convection. So convective heat transfer coefficient inside is 68.14 watt per meter square degree Kelvin at a bulk temperature of 311 Kelvin. So let us select the specific nodes at the inner side. These are the nodes at the inner side. Selected 3 different nodes, apply, and convective heat transfer coefficient will be equal to 68.14 watt per meter square degree Kelvin, 68.14 watt per meter square degree Kelvin at a bulk temperature of 311 Kelvin, 311. Done. Another boundary condition to be applied, that is convection at the outer surface, while atmospheric temperature is 255 Kelvin and convective heat transfer coefficient is 17.04 watt per meter square degree Kelvin. Let us select the specific nodes. Now again apply convection on nodes. Let us select the external nodes 3 6 9 11 and 12. The external nodes are selected. Okay, now we need to apply convective heat transfer coefficient as 17.04 and bulk temperature is 255 Kelvin. Okay, done. So we have applied all the boundary conditions. Next to that we need to solve it, and it will be done from solution, solve current LS. If everything is right, it will show solution is done. Okay, solution is done, so our results is perfect. We can see our results from general post processing. Okay, let us close it and let us see our results from general post processing. Plot results, contour plot, nodal solution, and we see degrees of freedom solution, nodal temperature. We will see temperature at different nodes. Okay, this is the temperature distribution. You can see left hand side temperature is very high. It is in the range of 309.694 Kelvin, and average outside temperature is 255.435 Kelvin. Now see the temperature distribution in a different way, in a better way. We can see the listing results and we can see temperature at different nodes. But at the same time, we can see the maximum temperature, minimum temperature also, right? So list results, nodal solution, DOF solution, nodal temperature. Okay, so we are having total 12 numbers of nodes and different nodes are having different temperatures. At node number 1, temperature is 309.69 Kelvin, and last node it is having 255.43. Let us see the node numbers from the element itself and see their temperatures, right? So plot nodes, and you can provide numbers to this one from plot controls, numbering. Let us provide node numbers to be on. Now these are the node numbers. You can see at different nodes we are having different temperatures. Node 1 is here at this location. That temperature is 309.69 degree Kelvin. Node 2, this one inside little bit, its temperature is 284.46. Node 3 at the exterior surface, its temperature is 259.88 Kelvin. And next one, again we are moving to the inner surface. At node 4 it is 309.62. Its temperature is high as it is in the inner surface, right? Then node 5 is having temperature of 283.77 Kelvin. Node 6 at the exterior surface, its temperature is 259.66 Kelvin. Again node 7 at the inner surface, its temperature is 308.27 Kelvin. Node 8 is having temperature of 279.93 Kelvin. Node 9 again at the exterior surface, its temperature is 258.68 Kelvin. Node 10, its temperature is 266.74 Kelvin. Node 11 again at the exterior surface, its temperature is 257.77. And finally node 12, its temperature is 255.43 Kelvin. And maximum temperature is occurring at node number 1, its temperature is 309.69 Kelvin. Right, now the same operation can be done using different method also. I'll show that one with different method. First of all, we'll save this one and see, we'll compare the results, right? Okay, remember the maximum temperature 309.69 at node number 1. Okay, let us save this part, close it. Now we'll perform the same analysis with a different method, right? So let us file, clear and start a new one. Do not read one. Okay, so we are starting again with the same method. It will be started with preferences. It is thermal analysis and preprocessor, element type, add, edit, delete. We need to add it. We are considering the same element, that is solid quad 4 node 55. Okay, let us close it. Now material properties to be provided is the same thing, right? Let us provide material properties, material models, structural, thermal, conductivity and isotopic. Its thermal conductivity is actually how much it is? 1.7307, 1.7307 watt per meter degree Kelvin. Okay, let us close it. Next to that, you need to start modeling. In this case, we'll be providing different types of modeling, and that will be created with areas, right? Areas, rectangle by 2 corners. We know that it is a annular space of 2 rectangular areas, and we need to create 2 rectangles. First one with x equal to 0 and y equal to 0. Width of the rectangle is 4 meter and height is also 4 meter. Apply. First rectangle is made. Now inside this one another rectangle to be made, and inside we need to see the coordinate of that one, right? At x equal to 1 and also y equal to 1, and width of the rectangle should be equal to 2 and height also will be equal to 2. This is the same model we are making. Okay, so 2 annular rectangles are made. Now from these 2 annular rectangles, the inner portion should be deleted or subtracted. That can be done from operate, booleans and subtract areas. And for subtraction area, first of all we need to select all the areas. Okay, next to that we need to select that area that to be subtracted. Let us select the inner area. Inner area is selected. Now if we click OK, that inner part will be deleted. Done. So this is the actual cross-sectional area of this chimney. Okay, now we need to mesh it. You can start meshing from here itself. Size controls, manual size, areas, all areas, and we need to provide the length of this one as 0.05 meter. Okay, Let us mesh it. Areas, free, pick all. Meshing is done. Now we can apply our boundary conditions. That can be done from loads, analysis type, new analysis. It is a steady state analysis and we need to define loads. Apply thermal convections on lines. Let us select inner lines. From inner lines, heat will be transferred by way of convection with 68.14 watt per meter square degree Kelvin at a bulk temperature of 301 Kelvin, right? Okay. The convective heat transfer coefficient is 68.14 watt per meter square degree Kelvin and bulk temperature is 311 Kelvin. Okay, done. Now another boundary condition to be applied, that is at the external surface. At the external surface, it will be transferred by way of convection with the convective heat transfer coefficient of 7.04 watt per meter square degree Kelvin and at a bulk temperature of 255 Kelvin, right? So again, apply thermal convection on lines. Let us select all the lines one by one. All the lines are selected. Okay. Now we need to apply convective heat transfer coefficient as 17.04 watt per meter square Kelvin and bulk temperature is 255 Kelvin. Okay. So our boundary conditions are applied. Next to that, we need to solve it. It will be started from solution. Solve current LS. If everything is right, it will show solution is done. It is showing solution is done. So everything is perfect. We can see our results from general processing. Okay. Let us close it and we can see our results from general processing. We need to see results from plot results, contour plot, nodal solution, DOF solution and nodal temperatures. We need to see temperature at defined nodes, right? You can see here maximum temperature is 309.668 Kelvin and minimum temperature is 255.389 Kelvin, right? Now we want to see the temperatures in the form of listing results also. List results, nodal solution, DOF solution, nodal temperature. Okay, you can see we are having a lot of nodes. We divided this one into 5113 numbers of nodes and maximum temperature is 309.67 at node number 461, right? These are the different ways of modeling, and in this case we don't know whether this is perfect or not, because the thing is, if we go on remeshing and remeshing again and again, the results will vary, right? And when convergence criteria will be achieved, we can say that our result is optimized, right? So with this one, we'll conclude our today's video. This was very simple finite element analysis of a chimney using ANSYS mechanical APDL. And in this video, we analyzed this chimney using two different ways, right? And finally, we got the temperature distribution throughout the chimney. Okay, so this is all about our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.